Welcome to Engineering with Rosie. Today's topic is part of the wind energy series, and we're going to find out about two different ways that you can regulate a wind turbine's power output: stall regulation or pitch regulation. So first, let's start by explaining what that means to regulate a wind turbine's power output. A wind turbine generates electricity from the wind. Wind moving over the wind turbine blade generates a lift force at a distance from the hub. This force times distance creates torque, which is what turns the blades. The wind turbine blades are connected to a shaft, which is connected to a generator. The generator takes that mechanical energy from the rotating shaft and converts it to electricity. But the amount of power the generator can handle is limited, and when wind speeds are very high, there is more power available than the generator can handle. And so to avoid overloading it, there needs to be a way to reduce the amount of power coming from the blades to the generator. And there are two main ways of doing this: stall regulation or pitch regulation. The first way, most common on early turbines up to about the 1990s, is stall regulation. So what is stall? The aerodynamic effects that make a wind turbine blade rotate are the same as the effects that make an aeroplane wing fly. When an airfoil is inclined relative to airflow, it creates a lift force that acts perpendicular to the airflow, and also a drag force that acts parallel, opposite to the direction of the wind. In aerodynamics, the amount of incline relative to the wind is called the angle of attack. An increase in this angle increases the amount of lift, but only up to a point, and that point is called the stall angle. For an aeroplane to climb, the lift force needs to increase, so the pilot will pitch the front of the aeroplane up. But she needs to be careful not to climb too steeply, because if she increases the angle of attack beyond the stall angle, the lift force will suddenly decrease and the aeroplane will start to drop. What's happening here is that moderate angle of attack, the air flows smoothly along the airfoil, and the inclination causes some rotational component to the flow, which causes low pressure on the top of the profile relative to the bottom. The profile gets pushed up by the high pressure on the bottom and pulled up by the lower pressure on the top. But at a certain point, the airflow won't stay attached to the profile, but will instead separate. And when it does that, there is suddenly less circulation and so less lift. At the same time, the separated flow is very turbulent, which means that it is violently swirling. This suddenly increases the drag force at the same time as the lift force decreases, and this effect is called stall. On a stall-regulated wind turbine blade, this sudden decrease in lift force means that there is less torque turning the blades. Okay, so now we know what stall is, and we know why it decreases the power produced by a turbine. But how do they make sure that the blade stalls when wind speeds get too high? Well, actually, you don't need to do anything. If the blade is fixed in place, then as the wind gets stronger, the angle of attack will automatically increase towards stall. I'll explain that a bit more because maybe it's not that obvious why that happens. I mentioned that a wind turbine blade flies just like an aeroplane wing does, but the environment that it's operating in is a bit different because the turbine blade is rotating. In addition to the airflow in the wind direction, the blade also sees airflow in the direction of rotation. To find the local angle of attack, you need to add these two wind speed vectors to get the resultant wind speed and direction. As the wind speed increases, it changes the angle of attack closer to stall. If the blades are fixed and the rotational speed stays the same, then when the wind speed gets high enough, the blade will start to stall, which reduces the power. This is a very simple way to regulate power. The blades can be rigidly attached as they don't need to twist to change the angle, since that happens automatically as the wind speed increases. But there are also some big disadvantages. When the blade stalls, it causes turbulent swirling airflow, which is quite unpredictable and causes a lot of vibrations and extreme forces that can shorten the lifetime of the blades and other turbine components. So let's move on now to the second way that you can regulate power on a wind turbine. That's called pitch regulation. Pitch regulated blades deal with the problem differently. As the wind speed increases to the point where power needs to be regulated, instead of allowing the angle of attack to increase to stall, a pitch A pitch regulated blade will actually twist the blade to decrease the angle of attack. This also reduces the lift force, and so it limits the power. But because it avoids stall, the airflow stays attached to the blades, so there are less vibrations and the extreme forces are lower for a pitch regulated blade compared to a stall regulated one. But to be able to use pitch regulation, you need to be able to twist the blades relative to the airflow. This means you can't rigidly attach the blades at the hub. They need to be mounted on bearings to be able to turn. And that is the main reason why it took engineers a while to move to pitch regulation as the norm. The pitch bearings operate in a really challenging environment compared to most applications for bearings. They need to be able to transfer really big forces from extreme winds, and they need to have a long design lifetime. It's very difficult to replace a pitch bearing, so they should last the entire life of the wind turbine, which is usually 20 to 30 years. There are other advantages though to being able to twist the blade aside from pitch regulation. You can also twist the blades to start up in low wind speed, you can twist the blades out of the wind in very high wind speeds, and you can twist it to use it as a brake. In turbines that had fixed blades, they had to add tip brakes, and that meant running hydraulics through the length of the blade, which was not necessarily reliable or easy to maintain. So for large modern turbines, the benefits of being able to twist the blades mean it's worth the added complexity. So these days, the only stall regulated turbines you see are either really old or sometimes in small turbines for home or farm usage where simplicity is really important. So there you have it. Those are the two ways that you can regulate wind turbine power. Let me know in the comments if there was a concept that you found difficult to understand, or maybe there's another concept you would like me to cover and I can make a new video on that. And if you would like to see more videos like this, please like and subscribe and share with your friends. I'll see you next time.